Let's look at some sentences. What do you notice among these sentences? The conclusions of these sentences are not certain. Let's examine the first sentence. Here, we cannot say that Rahul will get a first class in the annual examination. He may or may not get a first class. Thus, the prediction of getting a first class depends on his performance. Similarly, we cannot predict the happenings described in the other sentences. In such sentences, the words probably, doubt, and chance involve an uncertainty. These words are all synonyms used to indicate the term probability. Probability is defined as the likelihood of something occurring. Now, let's perform a couple of activities. In the first activity, we'll find the sum of the measures of the angles of some quadrilaterals. We know that the sum of the measures of the angles of a quadrilateral is 360 degrees. If we perform the same activity for any quadrilateral, the result will be the same. In the second activity, we'll measure the sides of some equilateral triangles. We know that the sides of an equilateral triangle are equal. Here also, we'll get the same result if we perform the activity any number of times. Such activities are called experiments. In the above cases, we can predict the results. However, there are some experiments where we cannot predict the results. Let's look at an experiment where a die is rolled 10 times. Every time we get a result. Can you predict the result if you roll the die once again? This cannot be predicted because we do not know what we will get. It can be any number from 1 to 6. Such experiments are called random experiments. Mathematically, a random experiment is an experiment that has more than one possible result, and it is not possible to predict the result in advance. The possible result of a random experiment is called its outcome. For example, the outcomes of rolling a die are 1, 2, 3, and so on. The outcomes of tossing a coin are heads and tails. A random experiment can have any number of predictable outcomes. The set of all the outcomes of a random experiment is called sample space. It is denoted by the capital letter S. The sample spaces of rolling a die and tossing a coin are represented as shown. An element of a sample space is called a sample point. In other words, every outcome of a random experiment is also called a sample point. Let's perform an experiment where two coins are tossed at once. Each coin can turn up either heads or tails. Therefore, the possible outcomes may be heads on both the coins, heads on the first coin, and tails on the second coin. Tails on the first coin, and heads on the second coin. And tails on both the coins. Therefore, the sample space of the experiment is as shown. The outcomes of this experiment are the ordered pairs of the outcome of the first coin and the outcome of the second coin. For the sake of convenience, we may omit the commas from the ordered pairs. In set builder form, this can also be written as S is equal to x comma y, such that x is the outcome of the first coin and y is the outcome of the second coin. A collection of the outcomes of a sample space is called an event. In other words, a subset of a sample space is called an event. In this example, some of the events are shown. In this module, you will learn about the different types of events in probability. Let's consider an experiment of throwing a die once. The sample space associated with this experiment is 1, 2, 3, 4, 5, and 6. Which of these outcomes are even numbers? They are 2, 4, and 6. This implies the outcomes that correspond to the occurrence of even numbers are 2, 4, and 6. Similarly, the outcomes that correspond to the occurrence of odd numbers are 1, 3, and 5. Such outcomes are called events. Therefore, an outcome or a collection of outcomes is called an event. Let's denote the events by E and O. Here, we notice that sets E and O are the subsets of set S. In other words, any subset of a sample space is called an event. If S is a sample space, then the null set and S are the proper subsets of S. Hence, the subsets are two events in S. Let's look at an experiment where a die is rolled. Let E be an event. A number less than 3 appears. If the outcome is either 1 or 2, then we say that event E has occurred. If the outcome is other than 1 or 2, then we say that event E has not occurred. Events can be classified into sure, impossible, simple, and compound events based on the elements they have. Let's consider an experiment where a coin is tossed. In this case, the occurrence of an event of a head or tail is sure. Such events are called sure events. In general, if S is a sample space, then the whole sample space is called a sure event. In dropping a ball from a height, the event that it will hit the ground, and in throwing a die, the event of getting a number from 1 to 6 are examples of sure events. In an experiment, a die is thrown. In this case, the event of getting a number that is divisible by 7 is not possible. Such events are called impossible events. In fact, the event null set of a sample space will never happen. In general, if S is a sample space, then the event phi is called an impossible event. Some examples of impossible events are the event of selecting an apple from a bag consisting of 10 oranges, and when a ball is thrown up, the event that the ball will stay in air. Let's consider a sample space S of an experiment of rolling a die and its associated events as shown. Here, we see that each event contains only one sample point. Such events are called simple events. An event of a sample space with only one sample point is called a simple or elementary event. The number of simple events of a sample space of n sample points is n. An event that has more than one sample point is called a compound event. Let's consider the sample space of an experiment of tossing 2 coins. Events E1 and E2 associated with sample space S are shown. both the events have more than one sample point. Therefore, the events are compound events. In this module, you will learn to perform different operations on events. We know that a sample space and its associated events are represented in the form of sets. Thus, like set operations, we can combine two or more events by using analogous set notations. Let's consider a sample space S and two events of S, A, and B. The basic algebra of events includes complementary event, event A or B, event A and B, and event A but not B. Let's begin with complementary events. The complement of an event A is the event consisting of all the outcomes of the sample space that do not correspond to the occurrence of A. It is also called event not A. The complement of A is denoted by A dash or A bar. Let's consider the sample space shown when a die is rolled. A equal to 3, 6 is an event multiple of 3. Clearly, for outcome 1, event A has not occurred. However, we can say that not A has occurred. Similarly, for every outcome that is not in A, we can say that not A has occurred. Thus, the complementary event not A to event A, or A complement, is 1, 2, 4, and 5. In general, complementary event not A can be written as A such that A belongs to S and A does not belong to A. Next event, A or B, is analogous to the union operation on sets. If events A and B are associated with sample space S of an experiment, then event A or B contains all the elements that are either in A or B or in both. It is denoted as shown and is read as A union B or A or B. In general, event A or B is equal to A union B, which is equal to A such that A belongs to A or A belongs to B. Consider the sample space shown where a die is rolled. Let event A be the occurrence of prime numbers and event B be the occurrence of even numbers. Now, event A or B can be obtained as shown. Let's look at another experiment where two coins are tossed simultaneously. The sample space is obtained as HH, HT, TH, and TT. Consider these events associated with S. Therefore, the outcomes of the events are obtained as shown. Now, event A or B is obtained as HH, HT, TH, and TT. Here we notice that event A or B is equal to the sample space of the experiment. Such events are called exhaustive events. Two events A and B in a sample space S are said to be exhaustive if A or B is equal to S. In general, events E1, E2, E3, and so on in a sample space S are said to be exhaustive if the union of all the events is equal to S. In other words, events E1, E2, E3, and so on are said to be exhaustive if at least one of them necessarily occurs whenever the experiment is performed. If events A and B are associated with the sample space S of an experiment, then event A and B contains the elements that are common to both A and B. It is denoted as shown and is read as A intersection B or A and B. Event A and B can be written as A such that A belongs to A and A belongs to B. Consider a sample space of rolling 2 dice. Let events A and B be associated with S. The outcomes of events A and B are obtained as shown. Now, event A and B can be obtained by identifying the common elements present in both the events. Let's consider another experiment where 3 coins are tossed simultaneously. The sample space associated with the experiment is as shown. Now, consider 2 events A and B. Event A is getting at least 2 heads. Event B is getting at least 2 tails. Therefore, the outcomes of the events are obtained as shown. Now, event A and B is a null set because there is no common element between A and B. This implies that both the events cannot occur at the same time, and thus they are exclusive to each other. Such events are called mutually exclusive events. 2 events A and B in a sample space S are said to be mutually exclusive if A intersection B is equal to null set or A and B are disjoint sets. In general, events E1, E2, E3, and so on in a sample space are said to be mutually exclusive if they are disjoint sets. However, some mutually exclusive events in a sample space are exhaustive. For example, getting even numbers and odd numbers in an experiment of rolling a die. Such events are called mutually exclusive and exhaustive. In a sample space S, if any pair of 2 events EI and EJ are disjoint, and the union of all the events is equal to S, then all the events are called mutually exclusive and exhaustive. If events A and B are associated with sample space S of an experiment, then event A but not B is the event of all the elements of A but not in B. It is denoted by A minus B and read as A but not B. Therefore, event A but not B is equal to A such that A belongs to A and A does not belong to B. Please remember that event A but not B is equal to the event A and B complement. Let's consider an experiment of throwing 2 dice simultaneously. Consider events A and B associated with the experiment. The outcomes of events A and B are obtained as shown. Now, event A but not B is the elements of A that are not present in B. In this module, you will learn to define the axiomatic approach to probability. You will also learn to prove basic theorems related to probability. We know that an event is an outcome or a collection of outcomes. But how can you quantify the chances of an event happening? Mathematicians attempted to measure the happenings of an event using probability theorems. We know the classical theory and the statistical theory of probability. In the classical theory of probability, the probability of an event is equal to the number of outcomes favorable to the event divided by the total number of possible outcomes. In this theory, the number of outcomes is finite and all the outcomes are equally likely. However, in the statistical theory of probability, we find the probability of an event happening based on the observations and the data collected. Neither theory can be applied to experiments that have an infinite number of outcomes. Furthermore, in the classical as well as the statistical theory, it is assumed that all the outcomes are equally likely. That is, the outcomes are equally probable. This is logically incorrect. For example, the event of getting at least a head in an experiment of tossing of two coins simultaneously. Therefore, A.N. Kolmogorov, a Russian mathematician, developed a new theory of probability in 1933. This is called the axiomatic approach to probability. In this approach, some axioms or rules are laid down to interpret probability. Let S be the sample space of a random experiment. According to the axiomatic approach to probability, the probability P is a real valued function whose domain is the set of all the subsets of sample space S, and the range is the interval 0, 1. Here function P satisfies some axioms. Let's take a look at them. The probability of any event, say A, is non-negative, that is, P of A is greater than or equal to 0. The probability of the sampled space S is 1, that is, P of S is equal to 1. If A and B are mutually exclusive events, then P of A union B is equal to P of A plus P of B. Let's consider an experiment where a die is rolled. The sample space associated with this experiment is shown. Thus, the probability of the event getting 1 is 1/6. The probability of the event getting 2 is 1/6, and so on. In all the cases, we notice that the probabilities of the events are equal, which is 1/6. We also notice that the probability of each event lies between 0 and 1. Hence, the probabilities of the events satisfy axiom 1. Now, let's add the probabilities of all the events, which is equal to 1. This implies that the probability of S is equal to 1. Hence, the probabilities of the sampled space satisfy axiom 2. Now, let's consider a coin is tossed once. The coin has 3 times the chance of falling heads up as it has of falling tails up. Therefore, P of H is equal to 3/4, and P of T is equal to 1/4. The values of the probabilities lie between 0 and 1. On adding the probabilities, we get 1, which is the probability of the sample space. Now, we'll prove some theorems related to probability. Let's begin with the theorem, which states the probability of an event that cannot occur is 0. That is, P of phi is equal to 0. Consider two events A and B such that both A and B are null sets. Thus, A intersection B is equal to phi. This implies that events A and B are mutually exclusive. Hence, P of A union B is equal to P of A plus P of B. This implies P of phi union phi is equal to P of phi plus P of phi. On simplification, we get P of phi is equal to 0. Hence, the probability of an event that cannot occur is 0. The next theorem states that if A is an event in sample space S, then 0 is less than or equal to P of A is less than or equal to 1. Given that A is an event in sample space S, we know that phi is a subset of any event. Thus phi is a subset of A, which is a subset of S. Therefore, P of phi is less than or equal to P of A, which is less than or equal to P of S. We know that the probability of a null set is 0 and the probability of a sample space is 1. Hence, the probability of an event of a sample space always lies between 0 and 1. Let's prove a theorem on the probabilities of equally likely outcomes. If E is an event in a sample space S containing n sample points that are equally likely, then P of E is equal to 1 divided by n. Let P of E be x. Consider that E1, E2, E3 and so on are the elementary events that contain each sample point in sample space S. Thus, the events are mutually exclusive and exhaustive. Therefore, the union of the events is equal to S. The probability of the union of all the elementary events is equal to the probability of the sample space. It implies that the sum of the probabilities of all the elementary events of S is equal to the probability of the sample space. Since sample space S contains equally likely sample points, the probability of each event containing a sample point will be x. Thus, we get sum of n number of x's is equal to 1. That is, nx is equal to 1. Therefore, x is equal to 1 divided by n. Hence, P of E is equal to 1 divided by n. S is a sample space containing n sample points, and A is an event in S containing m sample points. If each outcome is equally likely, then P of A is equal to m divided by n. Let E1, E2, E3 and so on be the elementary events of S containing each of the m sample points of event A. We know that the events are mutually exclusive and exhaustive. Therefore, the union of all elementary events of event A is equal to A. The probability of the union of all elementary events of A is equal to the probability of event A. This implies the probability of A is equal to the sum of the probabilities of each of the elementary events of A. Since we know that S contains n sample points, the probability of each of its sample points is equal to 1 divided by n. Therefore, the probability of event A is equal to m divided by n. In this module, you will learn to prove theorems related to probability. Let's prove a theorem on the probability of event A or B, where A and B are events of a sample space. This theorem states that if A and B are any two events of sample space S, then the probability of event A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Let's observe the figure. From the figure, we notice that B minus A union A intersection B is equal to B. Similarly, B minus A intersection A intersection B is equal to phi, which is a null set. It implies that events B minus A and A intersection B are mutually exclusive. Now, P of B is equal to P of B minus A union A intersection B. Since events B minus A and A intersection B are mutually exclusive, P of B is equal to P of B minus A plus P of A intersection B. This implies P of B minus A is equal to P of B minus P of A intersection B. Let this be equation 1. Again, from the figure we have A union B minus A is equal to A union B. A intersection B minus A is equal to phi. This implies events A and B minus A are mutually exclusive. Now, P of A union B minus A is equal to P of A union B. Since events A and B minus A are mutually exclusive, P of A union B is equal to P of A plus P of B minus A. By using equation 1, we get P of A union B is equal to P of A plus P of B minus P of A intersection B. If A and B are two mutually exclusive events in sample space S, then A intersection B is equal to phi, and therefore P of A union B is equal to P of A plus P of B. If A and B are any two events in sample space S, then P of B minus A is equal to P of B minus P of A intersection B, and P of A minus B is equal to P of A minus P of A intersection B. Let's look at an example. Find the probability of getting a prime number or an odd number when a cubical die is rolled. Let A be the event of the occurrence of a prime number. It will consist of the numbers 2, 3, and 5. Let B be the event of the occurrence of an odd number. It will consist of the numbers 1, 3, and 5. Thus, A intersection B is the event of the occurrence of an odd prime number and consists of 3 and 5. Now, the probability of A is equal to 1/2. The probability of B is equal to 1/2. The probability of A intersection B is equal to 1/3. Now, A union B is the event of the occurrence of a prime number or an odd number, which is 1, 2, 3, and 5. The total number of possible outcomes is 6. We know that P of A union B is equal to P of A plus P of B minus P of A intersection B. On substituting the values of P of A, P of B, and P of A intersection B, we get 2/3. Hence, the required probability is 2/3. If A, B, and C are any three events in a sample space, then P of A union B union C is equal to P of A plus P of B plus P of C minus P of A intersection B minus P of B intersection C minus P of C intersection A plus P of A intersection B intersection C. To prove this, let's consider P of A union B union C. This is equal to P of A union B union C. By using the theorem on the probability of an OR operation of two events, we get these steps. Since A intersection B intersection A intersection C is equal to A intersection B intersection C, we get P of A union B union C is equal to P of A plus P of B plus P of C minus P of A intersection B minus P of B intersection C minus P of C intersection A plus P of A intersection B intersection C. Hence the theorem is proved. Now, let's prove a theorem. If A is an event of a sample space, then A' is the complement of event A, and P of not A is equal to 1 minus P of A. We know that events A and A' are mutually exclusive and exhaustive. This implies A union A' is equal to S and A intersection A' is equal to phi. Now, P of A union A' is equal to P of S. By using the axiomatic approach to probability, we get P of A plus P of A' is equal to 1. This implies P of not A is equal to 1 minus P of A. Hence, the theorem is proved. Let's look at an example. If the probability of event A is 3 divided by 8, then the probability of event A' is equal to 1 minus the probability of A, which is equal to 5 divided by 8.